Yeah, drop, hey, huh.
Yo, what's up guys, this is 𝗪𝗥𝗟𝗟𝗟 and today we're playing
Catch me outside, how about that?
from PicoCTF, another binary exploitation challenge. So let's go. We download the files right here. We have heap_edit, 𝗙𝗘𝗟𝗟𝗟𝗪 and a makefile. Cat makefile, we see that the challenge is linked to the current path. Okay, it has no pi. And let's see, it's 𝗪𝗔𝗧𝗪𝗟 heap_edit and we try to run it. And we get this error. In another challenge I had tried to patch it like this, patch elf, and don't do that because I spent like the whole day trying to debug it and this was a wrong approach. Instead we should do something like pwn_init, like this. What will this actually do? It will use the current libc and it will create a heap_edit patched with the correct dynamic linker and libc. So we run it. And we see now that we have a heap_edit patched and the correct LD for our current libc. And let's try and run the program. We have heap_edit. Yeah, remove heap_edit. So we run heap_edit patched and we see we got a segmentation fault. And why did this happen? If we go inside the debugger, we see that the program tries to open flag.txt. And if it doesn't have it, with the f gets like this, the program will crash. It does not check if it is null. And in this case it is null. So we just create a flag.txt like this, so it exists, and right now we run heap_edit, and we see you may edit 1 byte, okay, address, and the program exited. So inside the decompiler right here we see we have some stuff, the canary, and it opens flag.txt. After that writes, this is a random string inside the random string buffer, and then we have a 𝗧 address which is initialized with 0, then 7 iterations. And this is, if you're familiar with it, this is a common tcache technique. So you allocate 7 chunks and then you start freeing like this. And we see if the 𝗧 address is null, which is null right here, it takes the allocated space value. And after that, at allocated space, it writes, congrats, your flag is blah blah blah. It writes flag to allocated space. And then it allocates another space with 𝗪𝗔𝗟𝗟𝗟𝗪 and writes, sorry, this won't help you, blah blah blah. And then we have 2 frees, allocated space and another allocated space. And right here we see we have printf address, so we can enter an address and then a value. And we see that it goes to 𝗧 address, and actually address is the index. We can write the offset and what value right here. And this is, if you see, this is %c, it's really small, but believe me, it's %c, so you can actually write 1 byte only. And then we have another malloc in the end, and it puts last allocated space plus 0x10. Okay, we got a small glimpse of the program from the decompiler, but let's go inside the debugger and play. So if we do the main, we see lots of stuff here as we saw. I'm gonna set a breakpoint just right after the scanf functions when we enter the address and the value. So b main plus this, and we run the program. Address, let's say 0, and value, let's say a. So we are exactly right after the second scanf, which is the value. And right here we see this is the address, like the base address we start writing. And this is the byte we wrote. Let's try something different. For example, if we do 100 and here b, we see that the value has changed. Now we have this address and this is the byte we write. So how can we abuse that? We know that we can write wherever we want, like this, and 1 byte to whatever we want. So let's take a look at the heap right now. Okay, tcache beans, we see your flag is here, blah blah blah, flag, 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 flag. And if we continue a bit, right here it writes our byte. So we have written it, this again, and we see our b is right here. So we can actually write wherever we want here. And also on the top we see another one here, some stuff. And here we see another address. And let's continue a bit. So it calls malloc again. And right here we see that it tries to take this address plus 0x10. So we need to find this address. Where is it exactly? We run the program again. Address, let's say 0, let's say b. and if we go viz, so we need to find this address 603890, and if we go on the top we see that here is our address 603890. So the program will call whatever has here, and our goal is obviously we can override it to something we want. As we saw, it will call something like this. Okay, so even if we overwrite it with something, we need to take into consideration that it will print whatever this has plus 0x10, and let's see, we have an offset like this. If we manage to call an address from here, it will print your flag is PicoCTF blah 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 instead of the random string that we do not want. And let's see, we have 603890. My goal here is to overwrite this, the last byte, with something, and when you add 0x10 to it, it will point somewhere here. So 6038, we have 6038 here, and boom, we see if we change the last byte from 90 to be 0, then it will add 0x10, so it will point right here, and it will start printing the flag. So this is our goal. Let's run again. 0 and B. So this is our initial offset, like this, and viz. So we need to take this and subtract the offset where this byte is. So it's actually 60, 20, 88, 0x 60, 20, 88. And we see that the offset is right here. Let's see for ourselves. So we're gonna run again and enter minus 5144, and then I'm gonna change the last byte to be, I don't know, whatever you want. Let's make it I, which is 69, and right here we overwrote it, and let's take a look at viz. And we see that we have successfully managed to override it with 69 instead of what it was. So our goal right here is simple. If we change this from 69, from whatever it was, to a null byte to 0, the program will have this address, and after that it will add 0x10, so it will start printing stuff from here, which is actually our goal. And let's start making our exploit to see if this works. I have my template here, and as we saw, the offset was minus, I think it was this, and right here we need a null byte. Let's see if our solver works. So Python solver, and we see that we have managed to get our local flag. Let's also try to do this remotely. And boom, we have a totally reliable exploit. So that was a challenge, guys. Okay, it had to do something with heap. We didn't need to know in-depth stuff about heap to exploit it, because we actually had the 𝗙𝗘𝗟𝗟𝗪 primitive. So if you found the video useful, leave a like and subscribe to the channel to support me. And have fun, and see you in the next video. Bye.